We're here with co-founder and CTO Taylor Perkins, who is here to shed light on the subject of high performance computing and how that might play into the role of an actuary. So, welcome, Taylor.
Thank you for having me.
First, I wanted to start with just defining the topic. This is a term that people may have heard of. They may have seen the acronym HPC thrown around. Could you give us some guardrails around what HPC is and how it might be defined?
Yeah, sure. So HPC stands for high performance computing. And at its core, high performance computing is a really broad term that basically just means processing data at a much higher speed than a single computer can. The overarching concept that unites all HPC architectures is a distributed workload that you're parallelizing across multiple computers. So whether that's in a grid, in the cloud, on premise, there's lots of different ways you can implement HPC, but that's the high level concept.
And you mentioned distributed workload. Are there key components to a typical HPC network or key terms that people should be familiar with when they're looking at these solutions?
Yeah, so you'll hear three key pieces of architecture. There's compute, which is the servers or computers actually doing the work. There's a network because all these computers have to talk to one another and share information. And then there's storage. So some kind of common way to store data so that all of the distributed workers can access this data. Those are the three sort of key architectural components at a high level. Obviously, there's a lot of different ways to implement that, but people will hear those three key components quite often if they're talking about HPC.
Are there different types or levels of HPC?
I'm not familiar with any formal sort of tiers or types or levels, but there are lots of different ways to implement HPC. An example is like a lot of times people use the term supercomputers almost interchangeably with HPC. And depending on the implementation, that may or may not be true because a supercomputer usually is still one computer. Although it's possible to create a supercomputer that actually has hardware connections, like at a very raw level, right, for really intensive calculations. And so that would be like a more almost hardware implementation versus something like a cloud HPC grid, which is heavily relying on the network and the shared storage and things like that, that these computers are not physically connected. That creates a different sort of infrastructure to implement your goals. And then there's also, of course, on premise, which is usually similar to the cloud, but you're limited to whatever resources are actually in your local network versus being able to scale things up on demand.
So that goes into another question of mine, which is how does this really differ from a large on-premise grid or your typical run-of-the-mill cloud computing?
You can run HPC on an on-premise grid. The disadvantages are typically you have to have all of those machines in your local grid. It's difficult to spin stuff up. You got to go buy a new server and have your IT install it and all this sort of thing. So getting more on-demand scaling can be difficult. So you generally have some sort of upper limit about how much compute you can reasonably run at a given time. Whereas on something like the cloud, there are technically limits, but effectively unlimited compute. The other difficulty here about doing something on-prem is it requires a lot more architecture than just having a bunch of computers, right? Like you need network infrastructure, you need some sort of shared storage again, which can be just other computers or other servers, or can be, in the cloud, there's a lot of sort of services that abstract the servers away so that you can just think about the storage and not about the number of cores you have and, sort of thinking about the hardware. Being able to have all of those different components is unique in that way. And even versus traditional cloud computing, which originally was basically just moving your on-prem servers into the cloud, and you're really thinking about individual servers. When you start to get into more of an HPC environment, you're thinking about a much larger ecosystem that involves not just servers, but also these other architectural components that add complexity. And a lot of the cloud providers provide services that make some of these things a little bit easier, where you're abstracting out some of the lower level concepts that you don't really need to worry about when you're thinking about networking and storage and compute as sort of those three separate components of the architecture.
I've seen another type of computing that purports itself to be very fast, GPUs. How do those play into the overall scene?
Yeah, so GPUs are kind of a specialized processing unit that are particularly good at certain types of math. And if used correctly, you can design your system to take advantage of those sorts of processing units. Artificial intelligence, machine learning applications can really benefit from this kind of stuff, which is why companies like NVIDIA now are doing so well because there's a lot of AI and ML going on, and they make GPUs, and those are really good at those kinds of calculations. So you can speed things up even further if you can take advantage of GPUs, and you could even combine them with an HPC type architecture if you have that specialized work that needs to be done. The disadvantages are that CPUs are better at general purpose workloads. So if you're doing a lot more than just math, if you're moving data around or in something like a web app or something, you need to render data or visualize things. GPUs aren't necessarily good at those more general purpose things. In HPC architecture, there's a lot of trade-offs there. Like if you need to be moving a lot of data around or passing data across networks and things like that while you're processing, then a lot of times GPUs aren't necessarily as helpful. But if you can isolate processing that is really optimized by GPUs and run that in an HPC grid, you could potentially get even better performance there as well.
So I think that leads into my next question of honing this in on our actuarial audience. Are there specific product sets or teams that you see benefiting the most from high performance computing runs?
Yeah, so the key about the benefits of HPC is work that can be parallelized. Anybody can benefit as long as there is parallelizable work to be done. We see this a lot for things like valuation runs or really large runs where the work to be done for each policy is completely independent of work for another policy. And so that means that every single policy can be parallelized. That's a really great example of something that can benefit greatly from an HPC grid. We've seen runtime reductions that are just insane, 90+% reduction in runtime because we can parallelize all of those policies across a grid. Now, that being said, there are more complex types of runs, like if you think about cash flow testing runs and things like that are more dynamic. There's work that has to be done sequentially in these cases because we have to get the result from this in order to feed calculations downstream. But even those can benefit from HPC clusters if done correctly, meaning that at each point in time, there is a bunch of parallelizable work that can be done. And then there are still restrictive points that have to be done sequentially. But as long as you can scale quickly to parallelize and sort of come back to the points at which you need to be done sequentially, you can still benefit greatly. So really large cash flow testing runs and things like that can also benefit from this type of architecture.
You hinted towards the types of efficiency gains that you might see. Are there benchmarks that you would expect an HPC architecture to deliver relative to a non-HPC run?
Yeah, so this obviously depends on the HPC architecture and the vendor and what all work is being done. We've seen up to 90+% reduction in runtimes. For something like a cash flow testing run or something that's more complex, you might expect a little bit less benefit than that. But you're still talking about taking things that might have run in hours or days down into where you're measuring those in minutes or maybe in the low order of magnitude of hours. That is the kinds of reductions that I would expect to see, depending on the complexity of the model and what you're trying to do and how much dependencies there are on sequential activities and that sort of thing. So the more work that you can parallelize, the better performance gains you're going to get.
As an actuary, if you're comparing a couple of different solutions that have HPC architecture, how would you prepare to vet those solutions? Are there questions or metrics that you would be asking in order to figure out which one might benefit you the best?
Yeah, so I think here it's really important to think about the sort of the overall process and how that HPC architecture is taking advantage of the grid and how it's architected. So you can ask a lot of questions like, what are the points of parallelization, for example? Because depending on your model, being able to structure it in a way that best takes advantage of that HPC grid is going to be really important. So that's sort of a little bit more of understanding the underlying architecture and designing the model correctly to take advantage of that, and then knowing that for each of the sort of HPC architectures that you're comparing. It's also important to consider what actual work is being done by the system on the HPC grid. So, for example, is there extra time uploading a model into the grid? Like, does that take extra time? There's obviously the running of the model itself. Then there's the writing of results. So are you just getting a flat file out, or is it writing to some sort of data warehouse ready to go on that? And these all impact total process time, right? Not just the time that the model is running. And this is an important consideration because if you're having to manually write results or manually move the things over to a reporting solution, then yes, you've got this HPC grid that's running your model really quickly. But if there's this sequential work that needs to be done of moving the results over, that obviously adds time. So thinking about the holistic picture about all the work that's being done, and then figuring out where the parallelization points are, I think those sorts of things are really important. And then the last thing I'll say is, as you're vetting a solution or multiple solutions, running some variety through, because different parallelization points will result in different types of runs running faster or slower and that sort of thing. So having a pricing run versus evaluation run, or large runs versus small runs, things like how far you're projecting out, projection period, things like that. Adding some variety there to get sort of a more holistic picture about the performance of the system is probably the best way to compare solutions.
So you've talked about parallelization being the key to HPC and a little bit about model design. Is there a general approach if somebody is looking to make their models more HPC friendly for the actuary to take?
Yeah, so it's hard to make general recommendations unless you're actually looking at a specific system. But in general, what you want to do is understand the configuration points of the system and where work is getting parallelized. Once you understand that, then you can design a model to take advantage of that. For example, a system like Slope is very flexible and there's a lot of different ways to do things. But if you want to take the most advantage of the parallelization of HPC, then you sort of want to structure your model in a certain way. Then you can actually design your model around that performance, and that'll give you the best results in the end because it sort of scales along those parallelization factors.
So I heard you mention Slope, obviously our platform has a high performance mode. Would you be able to talk a little bit about how that solution appears today?
So yes, Slope has an HPC implementation. We've designed it based on what I've been saying so far. There are interesting aspects of our implementation, though, things like uploading your model and writing results. This is all stuff that Slope does automatically as part of the run. So there is no sort of upload step. The running is then parallelized, and then there are some sort of unique aspects of Slope in that while the run is executing, we're already writing results to a centralized data warehouse so that results are immediately available at the end. And this actually presents some really interesting technical challenges in terms of the architecture, which make them unique among high performance computing architectures. So for example, the amount of data that a financial model generates is significantly more than the input data that goes into it, right? So you have your policy data and your assumption data that kind of goes into the model. But for every policy record that comes in, we might generate 5 million results on the back end, right? So when you start running a lot of volume through, you're generating a ton of data. And that presents some unique challenges, such as there aren't always cloud solutions that are designed for that sort of spiky workload where you're suddenly needing to insert a lot of results, right? So these are areas where we sort of had to build our own queuing mechanism to get results in as fast as possible and can take a really high volume of results and get those into a data warehouse quickly so that they're immediately available for reporting and analysis at the end. At a high level, it's very similar to what we've talked about, but there are unique aspects like that that make it, if you're somebody like me, it makes it fun to work on. But yet it's very, very complex architecture and we're constantly improving it. So
Do you see other actuarial platforms in the market implementing these HPC architectures, or is this something that's uniquely possible at Slope?
I've certainly seen aspects of it from others in the market. Some people offer grids and things like that. From what I understand, they're much more manual. So you need to allocate resources in order to distribute your workload on those resources and then tear those resources back down afterwards. Something that's unique about Slope is we do all that automatically. So you just hit run and then we distribute the workload and run it. And the reason that we're able to offer this in a much more sort of modern way or modern architecture is because Slope was designed to be cloud native from the beginning. So we didn't design the system to run on a single machine on your local laptop or anything like that. The system is designed to run in the cloud. And as a result, from day one, we started taking advantage of cloud architecture and all the resources that were available to us to distribute work across. And so it wasn't a big leap for us to then create an even more sort of complex HPC architecture that could distribute work in a much broader manner and reduce runtimes even further. We've been working on this from the very beginning, and Slope is designed from the ground up to take advantage of that sort of architecture.
Great. This has been really enlightening. So I appreciate you taking the time to share your knowledge on HPC with us.
Yeah, absolutely.